I'm going to be discussing one of the most important theorems in all of mathematics, and that is the Gauss's divergence theorem. The formal statement of the divergence theorem is that the closed oriented surface integral of a weighted vector field weighted by some function rho, v is the vector field here, over a surface. So that surface integral on the left side is equal to something called the volume integral on the right side. Now the volume is whatever the surface encloses. That's what this means. This means the surface is the boundary of the volume and V is the volume there. And so if you try to draw a picture here, you'll notice that information that's captured on the surface by talking about what's flowing in and flowing out of the surface, that's what the left-hand side is given by the right-hand side as something that happens within the surface. So what's happening at every little volume element d tau inside the surface, and I want you to imagine that this is inside the surface, is that there is a divergence operator. That gradient operator tells you how quickly things are either diverging from or towards that volume element. So if a good analogy is fish, if you have a net catching fish, the fish are darting this way and that from inside. Maybe there's a source of fishiness from within the net, or maybe there's a sink of fishiness like a little shark that's eating them all up. But basically you can, by observing the fish darting in and out of the surface, make an informed statement about what's going on within the volume and vice versa. From knowing the situation locally within the volume, you can make some informed decisions about the surface. So that's the reason why this is so important, because it connects two kinds of data. This is the data on the bulk, meaning volume data, and that's related to volume surface data on the left. So Gauss's divergence theorem essentially tells you how to explore something without getting into it. So you can explore a planet without actually landing on the planet or going into the planet. So this is why it's such a amazing tool in all of science. Now I want to focus on this first video on just the general principles and some of the applications involved in this thing. The proof is located in my notes, and other more advanced proofs can be found in specialized books. I would like to start with an example that's very familiar from physics, and that is the Gauss's law of electricity, or electrostatics to be more precise. If you've ever taken a beginning course in university physics, you'll know that this is a big deal there. Let me tell you how it's stated in university physics 2. The electric field dotted with the area vector over a surface is equal to the enclosed charge divided by epsilon naught. This quantity here is called the closed flux, sometimes denoted by the symbol phi e, closed. So another way of saying Gauss's law of electrostatics is that the enclosed flux only depends on the charge within. And not on the outside charges. There's a frivolous way of understanding Gauss's law in terms of daily analogies, and one of them is if you have a certain gallon jug of milk, it's like saying the amount of milk I have, which is 1 gallon, depends on the capacity of the gallon jug I'm holding and not on all the milk outside available in cows and supermarkets and so on. So that's a trivial way of thinking about something like this. Now these are called the integral forms of Gauss's divergence theorem, and that's the form in which I have written it. There's also the differential form version of it, and that would be this following. When you take the derivative of both sides by the first fundamental theorem of multivariable calculus, you'll end up getting something like this. The divergence of the vector field is going to be some source term. And that source term could be something like a charge density. I don't want you to confuse the charge density rho I'm about to write with this rho here. This rho is any function, sometimes called a scale function. But the source term I'm about to write is specific to electrostatics. So you write it as rho over epsilon naught. And then when you integrate both sides, when you so this is the divergence theorem, Gauss's divergence theorem in differential form. So let me integrate both sides with respect to the volume. So this is found in more advanced textbooks. We only teach this in UP2. How does this go into that? So that's a good exercise of using this. Let's take a certain volume and do a volume integral on this thing. So I have the triple integral over the volume of the divergence of the electric field is equal to 1 over epsilon naught, the triple integral over the same volume of the density function, the charge density, or the electric charge density function rather, times dV, the volume element. Well, this is none other than the charge enclosed over epsilon naught. So we have got the right hand side of Gauss's law as traditionally stated in lower level courses. What about the left hand side? This looks very different than that. Well, that's where you use the divergence theorem of Gauss as stated here. Now I'm going to choose my density function. So let me call this theorem 1. So in 1, choose the density function rho. So maybe I should call this something here. I'll call this rho d as a so that choose rho d equals 1, and then choose the vector field v to be the electric field, and I'm going to relabel some things. I'm going to call sigma the same as area vector A, and then d tau the same as the volume element dV, because these are the more common ways of writing things like surface and volume. This will be a very confusing thing to do in university physics too, because sigma stands for so many things like conductivity, and it also stands for the surface charge density, so you don't want to get confused. So even right here, I just realized there are two uses of rho. Rho is any density function, and then rho is also the charge density. So in this particular context, rho here is coulombs per meter cubed. That would be the SI units of rho in this particular context. Anyway, going back to the getting away from the many uses of the same symbol, let's now look at what this would look like using that divergence theorem of Gauss. This looks like the right hand side with rho d equals 1, so that should be equal to the left hand side. So I'm going to replace this with the double integral over the surface which bounds the volume of rho d is 1, so I just have to put what v is, the vector field, and that's E. So I get E dot d sigma, which is dA, equals q enclosed over epsilon naught. So in this manner, we have shown how to move back and forth from the differential form to the integral form of Gauss's law. There are many other areas where Gauss's law is used, and you can convert basically any law that you knew previously. Especially 1 over r squared laws are very useful. Let me show you how gravity gets converted to Gauss's law. So you take the force of gravity as discovered by Newton. You have the Newton's gravitational constant times the mass of the first object times the mass of the second object. I'm going to write the mass of the test object as little m, and that's divided by r squared. So the field as such is explored by this test object, and the gravitational field G is given by dividing both sides by m. So the gravitational field G ends up being capital G Newton. That's Newton's gravitational constant. I believe it has value, the way I remember it, is 2/3 times 10 to the minus 10 SI units. You can easily figure out the units by looking at this. And divided by r squared. So whenever you have this r squared type behavior, you can be guaranteed some interpretation of enclosed. So Coulomb's law is behind this thing here. So Coulomb's law, for those who need a refresher, is the electric force is K times Q, the test mass, times the source mass divided by r squared, and that's equal to Q times the electric field. So if you divide both sides by the source, by the test charge, you're going to get the electric field, which is K capital Q over r squared, and that leads to the enclosed phenomenon. So likewise, we expect this to have some enclosed phenomenon in Gauss's law, and let's do that. Let's find out what the corresponding Gauss's law would be for this particular example. This is a good exercise. So I'll say the gravitational flux enclosed in the closed surface, which is defined to be the closed oriented double integral over the surface, which is the boundary of the volume you're considering. The gravitational vector dotted with some area vector d sigma. Well, what's that going to be? If you put this quantity here into this thing, it'll turn out to be, and I won't show you the proof of this, it's a straightforward exercise in one of the homework problems. When you take a 1 over r squared type function and put it in there, you're going to get 4 pi gn times m. And then you can make this a law of nature by writing m enclosed. So this shows that the gravitational field only depends on the enclosed mass. Let's actually use this as an example to figure out what the gravitational field would be inside the Earth. So that's a classic problem in university physics for electric field, but we'll do the same thing for gravity field, because gravity field is less taught at undergraduate curriculum. So I'll write this as r. The radius of the planet, if you will, is capital R, and we have to find what the left hand side would be, and the right hand side would be the mass enclosed. Let's assume, for the sake of convenience, the planet has got a uniform density. So this density is now the third meaning of density, and this is kg per cubic meter. The third meaning for the symbol rho in this short video. So you can see how symbols can get very confusing unless you tell people what the context is. Now, what I'm going to do here is look at the gravitational field. It's going to be pointing inward by symmetry everywhere, and the area vector is going to be pointing outward, radially outward everywhere. So g dot d sigma, let's simplify the left hand side of Gauss's law, is going to be, I'll remove the orientation because the inward normal has already been chosen. So I'll write it as g times d sigma times cosine of pi, which is -1, by the way. And that's 4 pi times gn, the mass enclosed. Now, if it's a uniform density, the density can be given by the total mass of the planet divided by the volume you're considering. And that's 4/3 pi little r cubed. And the, capital R cubed. And then the volume that you have is 4/3 pi little r cubed. So the 4/3 pi's cancel out. And this here is negative I can take the g outside because it only depends on r and not on theta or phi, which are the other coordinates in spherical geometry, and then just get integral of d sigma. And that's equal to 4 pi times g Newton mass r cubed over capital R cubed. Now, if I take this calculation over here, then I'm going to get negative gr. Well, the surface area of a sphere is just 4 pi r squared. And that's equal to 4 pi g Newton m r cubed over capital R cubed. The 4 pi's cancel out, and I'm left with this amazing result that the gravitational field inside the Earth, or any other planet, if you will, I'll transfer the minus sign over to the right side, is negative, cancelling out here, g Newton mass over r cubed times r. So it is proportional to r. If you want to go someplace where you'll be half your weight, you just have to tunnel under the Earth to half the radius of the Earth, and there the gravitational field will only be 4.9 meters per second squared, and you can be half your weight. That's a quick weight loss program, although I suspect the act of digging that deep into the Earth will cause real weight loss too.